Anyway, the one-way chi-square test. All right, so we're taking it back from scratch here. So this video and the next three videos will, so now you're immortalized in the video. Will take us through again the one-way chi-square, two-way chi-square, linear regression t-test, followed by the ANOVA. Okay, so I think we all know that the one that, well, I don't know, maybe not. I would think the weirdest one is probably the linear regression t-test, but the chi-square one, it's pretty straightforward as long as you have a sense of what you're supposed to be doing. The first thing you're always looking for whenever you're doing anything involving chi-square or ANOVA is you're looking for more than two categories or two sets of data, whatever it happens to be. So in this case here we have really three categories: yes, no, or no opinion. If it was just yes or no, then I mean I guess you could use a chi-square, but you would probably just use a population proportion test, right? So or two population proportion. Well, actually, in this case, it would be one population because the total would be the n-die. But anyway, so if we're going to do the chi-square test, we would need to make sure, or the ANOVA, we would need to make sure we have more than three categories, three or more categories. So when individuals in a sample of 150 are asked whether or not they supported capital punishment, the following information were obtained. We're interested in determining whether or not the opinions of the individuals, yes, no, no opinion, are uniformly distributed. So that's a GOF. All right, so uniform distribution. My hand got a little crazy there. All right, so uniform distribution equals GOF, goodness of fit. All right, and the reason, so it's chi-square, GOF. Our reasons for that are we're dealing with counts. Counts, not averages. All right, so think in terms of, associate chi-square with population proportion. The same general underlying theories come into play. Think, when you're thinking ANOVA, think testing claims about means. All right, so means go with ANOVA, population proportions go with chi-square. More than two categories. And I think probably the most obvious one is in the question when they're talking about whether it's a uniform distribution, implying that it's asking for goodness of fit. All right, so my null hypothesis, oh, I'm sorry, we're not there yet. The assumptions, right? So that's where our, what you call it, cheat comes into play. Again, you look at the back and you see that there's a lot of similar characteristics among the different types of hypothesis tests. The simple random sample is always going to be there. We have to make that assumption. And if you're asked to do a question like this, even if they don't state it, if it says determine if there's a uniform distribution, goodness of fit, or if it says specifically using a chi-square test or with a particular alpha value, even if it doesn't say it, you have to go through the motions, but you would account for that and say, but I'm suspicious about these results because it didn't say it was a simple random sample. All right, skewed distribution. Well, that I don't know that we could tell just by looking at it in this case, but typically when you look at data points, if you were to just plot these as a dot plot, you would have, or even just a bar graph, you would have three values, and you would expect there to be some sort of skewness to it because typically we're looking at some balance between yes and no, and then the no opinion usually goes off on its own. It's either really low or really high depending on the question. All right, so we can assume maybe not a chi-square, maybe not a skewed distribution, but definitely we can make a case that it's not necessarily normal. All right, so we'll assume skewed. And then the last one there is we're testing for homogeneity, independence, or goodness of fit. To be honest, that should be the first one. If you see any of those words or those phrases, we're talking about a chi-square situation. Right, so the null hypothesis, good fit for the population parameter. Goof.
I wrote goof as well.
I
wasn't even looking at the board.
That is one of my most common goofs. Yeah. That and putting extra e's at the end of words.
Oh.
You know, like anything that doesn't end in a vowel is gonna, for the most part, with me, end with a vowel. Yeah, I just feel the need to throw an e at the end. I don't know. Good fit for population.
Sometimes after I write the in a sentence, and then I have to think about what I'm going to write for the rest of the sentence, I write the again. And I end up with 2 vowels in a row.
That is recorded for you.
But that's a different one. But I could see myself doing that too. I bet I have done that. I just never thought about it.
Probably when I made a mistake.
Well, my thing is I'm always thinking about the next word while I'm still writing the first one, so that's why I went goof on that. So not a good fit. All right, but it is possible that we could say something like, in this case, you could go if you want. There would be nothing wrong with this. P1 equals P2 equals P3, because if there's going to be a uniform distribution, those probabilities should be roughly the same. All right, and so and the alternative to that would be at least one P is different. So in this case, you can go either way. What was the other one? I always forget. The homogeneity. You could even say that the categories are independent, categories are homogeneous. You can go in a number of different directions. All right, so this sketch doesn't really apply. This would be a chi-square. Degrees of freedom here would be what? 2. 3 categories, 2 degrees of freedom. We need the critical value of chi-square, which you go to the tables for. Good question. Doesn't say, so we're going with 0.05. 5.99. Now our test statistic chi-square would be the sum of O minus E squared divided by E. And for that, we go to the calculator. 5.99 is what it's supposed to be. My handwriting is awful. Now you'll do this with the chi-square GOF test on your calculator. I'm just going to do it with the list feature. So 40, 60, 50. Very basic calculation. What should my expected value be? Or expected values? 50, 50, 50. And it's only 3 of them, so we could just type it in. We don't need anything fancy with that. All right, so we need O minus E squared divided by E, so, oops, not a second, just enter. So L1 minus L2 squared divided by L2. So we get the sum of that, which I don't think we need to use the sum feature for. So that would be a 4. Which does not make it to the rejection area. So we would not reject the null hypothesis. So you did the chi-square GOF test, and what'd you get for the p-value? Cool. Cool.
It's only on the 84, right?
Only on 84, yeah. I'm not pausing the video. I want the whole world to know how long it's going to take you all to figure this out.
never used those.
This is
Nah.
my face. This is
I haven't figured out how to do it yet. So, I mean, I'm sure it's a lot easier than I think, but I think that would require me to actually listen to the videos too.
Where have you been posting these?
On the class website, the TCAN registration safety stuff.
135?
0.135.
Just
Okay, so 0.135 is our p-value. Insufficient evidence to reject the claim. We could say that the number of individuals per category is a good fit for the population distribution. Or we could say that there's no difference in the population proportions among the different categories. That flows a little better, so let me do that. That there is no difference in population proportions among the different categories. Therefore, the claim of a significant difference, or a difference, that there is a, we'll say significant, even though it's going to be redundant. The claim of a significant difference is false at the 0.05 significance level. Okay, so we can't say that there's a significant difference among the groups, so that's saying that any possible opinion is really just uniformly distributed or evenly distributed, however you want to say it. So the claim of uniformity is true. Or you could say data are uniform. So that is a classic case of deadlock when you're talking about opinion polls. You know, if you have 70-30 yes or no, and then the remaining, or well, no remaining in that case, so let me just make a less idiotic example. 50-20 yes or no, and then 30 undecided, then you could kind of make a case for it being yes. You know, you figure if you split the difference on the undecideds, maybe it would balance its way out that way. But here we're looking at a uniform distribution between yes, no, and no opinion. So then it's really, you can't make a claim one way or the other based on people's perceptions.